Imagine you could step through a doorway and instantly emerge 93 billion light-years away at the very edge of everything we can see. What would you find there? Another Earth? Alien civilizations? Or something so strange it would shatter everything we think we know about reality? Today, we're tackling the ultimate question. Could you actually travel to the other side of the universe? The answer involves wormholes, warp drives, and engineering challenges that make rocket science look like child's play. But first, we need to understand what we're actually talking about when we say the other side of the universe. Understanding our cosmic neighborhood. Let's start with what we can actually see, the observable universe. That's the bubble of space from which light has had enough time to reach us since the Big Bang is approximately 93 billion light-years in diameter. That's right, 93 billion, not 13.8 billion, which is the age of the universe. This discrepancy exists because space itself has been expanding while light has been traveling toward us. Think of it this way. Imagine you're standing in the middle of a giant balloon that's being inflated. You shine a flashlight toward the edge of the balloon. As the light travels outward, the balloon keeps expanding. So by the time your light reaches what was once the edge, that edge is now much farther away. That's exactly what's happening with our universe. The objects that emitted light 13.8 billion years ago, right after the universe became transparent, are now about 46 billion light-years away from us in any direction. We're sitting at the center of this observable sphere not because we're special, but because that's how observation works. Every point in the universe is at the center of its own observable universe. But here's where it gets really interesting. The observable universe is almost certainly just a tiny fraction of the actual universe. Beyond our cosmic horizon, there's likely much more universe that we simply can't see yet. The universe might be infinite, stretching on forever in all directions, or it might be finite, but so large that our observable portion is like a grain of sand on an infinite beach. So when we talk about traveling to the other side of the universe, we could mean several different things. We could mean the opposite edge of our observable universe, a journey of about 93 billion light-years. We could mean beyond the cosmic microwave background, the edge of transparency itself. Or we could be talking about reaching entirely different regions of an infinite cosmos, perhaps even parallel universes in a multiverse scenario. Each of these interpretations presents its own unique challenges, but they all share one fundamental problem: the sheer incomprehensible scale of the distances involved. To put this in perspective, our fastest spacecraft, Voyager 1, has been traveling for over 45 years and has only just barely left our solar system. At its current speed, it would take about 73,000 years to reach the nearest star, Proxima Centauri, which is only 4.2 light-years away. To reach the edge of our observable universe would require traveling distances that are literally trillions of times farther than the nearest star. Using conventional propulsion, we're talking about journey times that would span not just millions of human lifetimes, but potentially longer than the current age of the universe itself. This is where we need to start thinking outside the box, way outside the box. If we're going to make this journey, we need to either find ways to travel much, much faster, or we need to find shortcuts through the fabric of space and time itself. This brings us to some of the most fascinating concepts in theoretical physics. What if, instead of traveling through space at incredible speeds, we could manipulate space itself? What if we could create shortcuts through the very fabric of reality? Enter the wormhole, one of the most mind-bending predictions of Einstein's general relativity. Picture space-time as a flat sheet of paper. Now imagine folding that paper so that two distant points touch each other. A wormhole would be like poking a hole through both layers, creating a tunnel that connects two far-apart regions of the universe. The mathematics of wormholes was first explored in 1916, just 1 year after Einstein published his theory of general relativity. Austrian physicist Ludwig Flamm realized that the equations allowed for what he called white holes, theoretical time reversals of black holes. In 1935, Einstein himself, working with Nathan Rosen, elaborated on this idea, proposing the existence of bridges through space-time that we now call Einstein-Rosen bridges, or wormholes. A wormhole would consist of two mouths connected by a throat. You could enter one mouth, travel through the throat, and emerge from the other mouth in a completely different part of the universe, or even in a different universe entirely. The journey through the wormhole itself might take only minutes or hours, even if the two mouths are separated by billions of light years through normal space. But here's the catch, and it's a big one. Natural wormholes, if they exist at all, would be incredibly tiny. We're talking about 10 to the negative 33 centimeters, smaller than subatomic particles. And even if we could somehow find or create a larger wormhole, it would be fundamentally unstable. Without some form of exotic matter to prop it open, a wormhole would collapse faster than light could travel through it. This exotic matter would need to have negative energy density, essentially negative mass. It would need to push space apart rather than pull it together, the opposite of everything we've ever observed in nature. Some physicists have suggested that the Casimir effect, a quantum phenomenon that occurs between closely spaced parallel plates, might provide this negative energy, but we're talking about engineering challenges that are so far beyond our current capabilities that they might as well be magic. Kip Thorne, one of the world's leading experts on relativity and wormholes, has said that there are very strong indications that wormholes that a human could travel through are forbidden by the laws of physics. That's not exactly encouraging for our cosmic road trip, but let's not give up hope just yet. What if, instead of creating shortcuts through space, we could manipulate space itself to bring our destination closer to us? This is the basic idea behind the Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994. Instead of moving through space faster than light, which is impossible, the Alcubierre drive would contract space in front of a spacecraft and expand space behind it, creating a warp bubble that could travel faster than light while the spacecraft inside remains stationary relative to its local space-time. Think of it like this. Imagine you're standing on a moving walkway at an airport. You're not walking any faster than normal, but the walkway is carrying you forward at high speed. The Alcubierre drive would work similarly, except instead of a moving walkway, it would create a moving bubble of space-time. The beauty of this concept is that it doesn't violate Einstein's speed limit. The spacecraft never actually moves faster than light relative to its local space. It's the space itself that's moving, carrying the ship along for the ride. From the perspective of someone inside the warp bubble, the journey would be comfortable and relatively quick. No time dilation, no crushing acceleration forces, just a smooth ride across the cosmos. But once again we run into that pesky problem of exotic matter. The original Alcubierre drive calculations required negative energy equivalent to the mass energy of Jupiter. That's about 1.9 times 10 to the 27th kilograms converted entirely to energy. Even if we could somehow obtain this much energy, we'd need it to be negative energy, which, as we discussed, doesn't appear to exist in nature. Recent research has suggested ways to reduce these energy requirements dramatically. Some studies indicate that the energy needed might be reduced to something equivalent to the mass of a small spacecraft or even less. But we're still talking about exotic matter with properties that have never been observed. There's another problem with warp drives that's often overlooked. How do you steer the thing? If you're inside a bubble of warped space-time, how do you communicate with the outside universe to control where you're going? How do you even know when you've arrived at your destination? These might seem like minor technical details, but they represent fundamental challenges that we don't yet know how to solve. Both wormholes and warp drives remain firmly in the realm of theoretical physics. They're mathematically consistent with our current understanding of general relativity, but they require forms of matter and energy that may not exist. They're like blueprints for a house that calls for materials that haven't been invented yet. But let's assume, for the sake of argument, that some future civilization figures out how to create stable wormholes or build working warp drives. Even then, the journey to the other side of the universe would present challenges that go far beyond the propulsion system itself. Let's talk about the elephant in the room, or should I say the cosmic radiation in the spacecraft. Even if we solve the propulsion problem, traveling to the other side of the universe presents engineering challenges that make landing on Mars look like a weekend camping trip. First, let's address the most immediate threat to any cosmic traveler: radiation. Here on Earth, we're protected by our planet's magnetic field and atmosphere, which deflect and absorb most of the high-energy particles streaming through space. But once you leave Earth's protective bubble, you're exposed to the full fury of the cosmos. Galactic cosmic rays are the nuclei of atoms, everything from hydrogen to uranium, that have been stripped of their electrons and accelerated to nearly the speed of light by the magnetic fields of exploding stars. These particles can pass through practically anything, including spacecraft hulls and human bodies. They're like microscopic bullets, fired by the universe itself. NASA considers space radiation to be the most limiting factor for long-distance space travel. Exposure to galactic cosmic rays increases the risk of cancer, causes central nervous system damage, and leads to degenerative diseases. For a journey lasting decades or centuries, the cumulative radiation dose would be lethal many times over. You might think, well, can't we just build better shielding? The problem is that traditional shielding materials like lead actually make the radiation problem worse. When high-energy cosmic rays hit heavy nuclei, they create showers of secondary particles that can be even more dangerous than the original radiation. It's like trying to stop bullets with a material that causes them to explode into fragments. Some proposed solutions include magnetic shielding, essentially creating an artificial magnetosphere around the spacecraft. But the power requirements for such a system would be enormous, and we're still not sure it would be effective against the highest energy cosmic rays. Then there's the challenge of life support. The International Space Station, humanity's most advanced space habitat, requires regular resupply missions from Earth. For a journey to the other side of the universe, there would be no resupply missions, ever. The spacecraft would need to be a completely closed ecosystem, recycling air, water, and waste with perfect efficiency for potentially thousands of years. Every system would need multiple backups, and every backup would need backups. A single critical failure, a broken air recycler, a contaminated water supply, a failed food production system could doom the entire mission. We're talking about engineering reliability standards that are orders of magnitude beyond anything we've ever achieved. And speaking of food production, forget about packing sandwiches for this trip. A journey of this scale would require sustainable agriculture in space. The spacecraft would need to carry soil, seeds, and all the equipment necessary to grow food for potentially hundreds of generations of travelers. The agricultural systems would need to be completely self-sustaining, producing not just food, but also the materials needed to maintain and repair the farming equipment. But perhaps the most daunting challenge isn't technical at all, it's human. We're talking about a journey that would span not just lifetimes, but potentially thousands of lifetimes. The people who begin the journey would never see the destination, neither would their children, or their children's children, or their children's children's children, and so on for potentially hundreds of generations. This is the concept of a generation ship, and it raises profound questions about human psychology, sociology, and ethics. How do you maintain a sense of purpose and mission across centuries? How do you preserve technical knowledge and cultural identity? How do you prevent social collapse, civil war, or the complete abandonment of the original mission? History shows us that human societies change dramatically over much shorter timescales. The people who would arrive at the destination might be as different from the original travelers as we are from medieval peasants. They might not even remember why they're on the journey in the first place. There's also the question of genetic diversity. A generation ship would need to carry enough people to maintain a healthy gene pool for thousands of years. Population geneticists estimate that you'd need at least several thousand people to avoid the problems of inbreeding and genetic drift. But supporting thousands of people in space for millennia presents its own enormous challenges. And let's not forget about the psychological challenges. Imagine being born, living your entire life, and dying inside a metal can, hurtling through the void. No blue skies, no fresh air, no open spaces. Just the same corridors and chambers for your entire existence. The rates of depression, anxiety, and other mental health issues would likely be astronomical. Some science fiction stories suggest that the inhabitants of generation ships might forget they're on a journey at all, developing into isolated societies that view their spacecraft as the entire universe. While this might solve some psychological problems, it would also mean the failure of the original mission. Even with all these challenges, let's imagine that some future civilization manages to build a generation ship capable of surviving the journey. They've solved the propulsion problem, the radiation problem, the life support problem, and the human factors problem. They launch their ship toward the other side of the universe and begin the longest journey in human history. What would they find when they get there? This is where our journey takes a turn into the truly mind-bending. What exactly would you find if you somehow managed to travel to the edge of the observable universe? The most distant thing we can currently observe is the cosmic microwave background radiation, the afterglow of the Big Bang itself. This radiation comes from a time about 380,000 years after the Big Bang, when the universe first became transparent to light. Before this moment, the universe was so hot and dense that photons couldn't travel freely. It was like trying to see through fog so thick that light itself couldn't penetrate it. If you could somehow travel to the source of this radiation, to the edge of the observable universe, you wouldn't find a wall or a barrier. You'd find yourself in a region of space that looks pretty much like any other region of space, filled with galaxies, stars, and planets. The cosmic microwave background isn't a physical boundary, it's a temporal one. It represents the limit of how far back in time we can see, not a limit to how far space extends. But here's where it gets really interesting. If the universe is infinite, then traveling to the other side might be a meaningless concept. In an infinite universe, there is no other side. There's just more universe, stretching on forever in all directions. Every point is equally valid as a center, and there are no edges or boundaries. However, some cosmological models suggest that the universe might be finite but unbounded, like the surface of a sphere, but in higher dimensions. In such a universe, if you traveled far enough in one direction, you might eventually end up back where you started, like circumnavigating the globe. But even in this scenario, there wouldn't be an other side in the conventional sense. There's another possibility that's even more mind-bending: the multiverse. Some interpretations of quantum mechanics and cosmology suggest that our observable universe might be just one bubble in an infinite foam of universes. Each bubble would have its own physical laws, its own history, and its own destiny. If this is true, then traveling to the other side of the universe might mean leaving our universe entirely and entering a completely different reality. You might find a universe where the laws of physics are different, where time runs backward, or where the fundamental constants that govern matter and energy have different values. But let's address some common misconceptions about space travel and the universe's structure. Many people imagine the universe as having a center and edges, like a balloon being inflated. While the balloon analogy is useful for understanding cosmic expansion, it's important to remember that we're not on the surface of the balloon, we're inside it, and the balloon has no center from our perspective. Another common misconception is that faster-than-light travel would allow you to travel backward in time. While Einstein's equations do show a connection between space and time, the relationship is more complex than science fiction often portrays. Even if we could build a working warp drive, it wouldn't necessarily turn us into time travelers. There's also the assumption that the universe has been expanding into empty space, like an explosion in a void. But space itself is expanding. There's no outside for the universe to expand into. The expansion of space is fundamentally different from objects moving through space. Perhaps most importantly, we need to address the assumption that interstellar travel is just a matter of building bigger rockets. The energy requirements for traveling significant fractions of the speed of light are so enormous that they challenge our fundamental understanding of what's possible. Even with perfect efficiency, accelerating a spacecraft to just 10% of light speed would require energy equivalent to the entire annual energy production of human civilization. So could you travel to the other side of the universe? The honest answer is almost certainly not, at least not in any way that resembles what we typically think of as travel. The distances involved are so vast that they strain the very concept of distance itself. The energy requirements are so enormous that they might exceed the total energy content of entire stars. The timescales are so long that they dwarf the entire history of human civilization, and the engineering challenges are so complex that they make our most ambitious current projects look like children's toys. But here's the thing about human ingenuity: we have a remarkable track record of achieving the impossible. A century ago, the idea of splitting atoms was pure fantasy. 50 years ago, landing on the moon seemed like science fiction. Today, we're seriously discussing missions to Mars and the search for life on distant exoplanets. The theoretical physics underlying wormholes and warp drives is real, even if the engineering is currently impossible. Every year, we learn more about the fundamental nature of space, time, and energy. We discover new phenomena, develop new technologies, and push the boundaries of what we thought was possible. Perhaps the journey to the other side of the universe won't be made by biological humans at all. Maybe it will be undertaken by artificial intelligences that don't need air, water, or food and can survive for millions of years without aging. Maybe we'll develop ways to upload human consciousness into digital form, allowing us to travel as information rather than matter. Or perhaps the answer lies not in traveling to distant places, but in bringing distant places to us. Advanced civilizations might develop technologies that allow them to observe and interact with distant regions of the universe without physically traveling there. Quantum entanglement, wormhole communication, or technologies we haven't even imagined yet might make the universe effectively smaller without requiring us to cross vast distances. There's also the possibility that we're asking the wrong question entirely. Maybe the other side of the universe isn't a place you travel to, but a state of understanding you achieve. As we learn more about the cosmos, we might discover that the universe is far stranger and more interconnected than we currently imagine. The boundaries between here and there, between us and the universe, might turn out to be illusions created by our limited perspective. What we can say with certainty is that the quest to understand and explore the universe will continue to drive human innovation and discovery. Even if we never build a working warp drive or find a traversable wormhole, the attempt to solve these problems will lead us to new technologies, new understanding, and new ways of thinking about our place in the cosmos. The journey to the other side of the universe might be impossible, but the journey to understand the universe, that's a trip we're already on, and it's the most exciting adventure our species has ever undertaken. So, the next time you look up at the night sky and wonder what's out there on the other side of everything, remember that you're not just looking at distant lights. You're looking at the frontier of human knowledge, the edge of our understanding, and the beginning of the greatest journey our species will ever take. The other side of the universe might be unreachable, but the quest to reach it will transform us in ways we can't even imagine. And maybe, just maybe, that transformation is the real destination we've been searching for all along. Thanks for joining me on this cosmic journey. If you enjoyed exploring the impossible with me today, make sure to subscribe for more adventures at the edge of human knowledge. And remember, in a universe this vast and mysterious, the only thing more incredible than the questions we can answer are the questions we haven't even thought to ask yet.